This conference will now be recorded.
Hello everyone. So today we will discuss previous year's questions of JEE main exam, and that is from the unit equilibrium. Okay. So here we have a question for the given hypothetical reactions. Hypothetical reactions because it is mentioned X, Y, Y, Z, Z, Y, W like this. There is no exact chemical formulas given. So that is why hypothetical reactions, the equilibrium constant are also as follows given. So for the first reaction, that is the conversion of X to Y, the corresponding K1 value 1. Then for conversion of Y to Z, the corresponding K2 value it is 2. And when it is Z to W conversion, now the K3 value is 4. You have to find equilibrium constant for the reaction when X is converted to W. So if we add these three reactions together, what will happen? See, suppose reaction number 1, reaction number 2, and reaction number 3. So you have to arrange these three equations in such a way so that you can get the equation for which you have to find the K value, because you already know the K values for the three reactions. Now, depending on how you are arranging these three equations, depending on that, you will have the new K value for the reaction X conversion towards W. So it is very easy. See, if you add these three equations simply, then YY will be cancelled from both sides. Then ZZ will be cancelled from both sides. So what is left? Left is basically this equation. That is why it means when you are adding equation number 1, equation number 2 and equation number 3, then you are getting the new equation, which is X conversion towards W. Now, how we will arrange this K1, K2, K3? Now, don't think that K1, K2, K3, as you have added this equation, then K1, K2, K3, that will also be added. No, it doesn't work like that. Okay. So that is why what we will do here, basically here you have to multiply all these K values. That is K value for equation 1, K value for equation 2 and for 3. So when we multiply K1, K2 and K3, then you get the K value for this new reaction. So here it is 1 multiplied by 2 and then multiplied by 4. So what value you are getting? You are getting 8, which is the value for this new reaction, which is this one. Now why it doesn't work like this? Because K1 value, how we get? When we write any equilibrium constant expression, we write it product concentration divided by reactant concentration. And then for the second reaction, product concentration, which is Z, that is I am writing it for equation 2, divided by reactant concentration. So see, here when you write the equilibrium constant expression for this three reaction and you are multiplying, you can also do so for the third one, expression concentration for W divided by concentration for Z. So here you can see, here after cancelling the concentration of Z, numerator denominator, concentration of Y, numerator denominator, what is left? Left is concentration of W divided by concentration of X. So when you are multiplying these three equilibrium constant expression, then only you are getting concentration of W divided by concentration of X, and that is the expression of K nu. So here 8 will be the correct answer, that is option 3. We'll go to next question. The ratio of Kp by Kc for the reaction. Which reaction? Carbon monoxide, a half oxygen, we are getting CO2. Now look at this reaction carefully. It is already balanced, so you don't have to balance it. It is oxidation of carbon monoxide to another oxide, which is carbon dioxide. Now to answer this question, that is you have to find the ratio of Kp-Kc, you have to know the relationship between Kp and Kc. So what is this relationship? Kp is related to Kc by this relation. Let me write it. So Kp is equal to Kc. Kp means when equilibrium constant is expressed in terms of partial pressure of the reactants and products, and Kc means the equilibrium constant expression when you are writing the expression in terms of the concentration of the reactant and products. And R is universal gas constant, T is temperature in Kelvin. And what is this del Ng? Del Ng is difference in the number of moles Obviously gaseous moles. If it is liquid or solid, it is not applicable. That is why here I have written G. Del N G means all the number of moles of gaseous products, that is in the right hand side of the equation, minus the gaseous number of moles of gaseous reactants, that is in the left hand side. So del Ng value, if we find for this reaction, in the product side, what you have? You have 1 mole of CO2, which is gaseous. Look at the physical state, G. It is not L or S. Minus the number of moles of CO is 1. So this is for CO. And half moles of O2. This is for O2. This is for CO2. So what is the del Ng value? Del Ng value you are getting minus half, because these two are cancelled. Now if you put it here, Kc RT to the power minus half. Okay, you have to find the ratio of Kp by Kc. So bring Kc in the left hand side. So you are left with RT to the power minus half. Now if you write it in this way, RT to the power half 1 by, and you can also write it like this. So ultimately it is matching with which expression? It is matching with the last option. Okay. So that is why this will be the correct option. At minus 20 degrees centigrade and 1 atmosphere pressure, a cylinder is fitted with equal number of hydrogen gas, iodine and hydrogen iodide molecules. For the reaction given, H2 gaseous, I2 gaseous, equilibrium sign 2Hi. Equation is already balanced. You have to find the Kp value for the process, and the format is like this. X into 10 to the power minus 1, you have to find the value of X. Look at this. It is not that you have to find the value of Kp. Kp you have to express in this format, then only you can find the value of X. Universal gas constant value is given 0.082. So here, first of all, we will find out that here we will write the expression in terms of Kc. Now all these are gaseous, and if we see the del Ng value, look at this, number of gaseous products moles 2, same expression that we have used in the last question. For hydrogen it is 1 mole, for iodine it is 1 mole. So del Ng value is 0. That means, remember the expression Kp is equal to Kc RT to the power del Ng. Now this value is 0 means Kp will be equal to Kc. You have to find Kp. But if you can somehow find Kc, then also it is fine. Because here doing that is the calculation of Kc is easier compared to Kp. So that is why directly I am not finding Kp. But first I have just checked from this relationship what is the relationship between Kp and Kc, and what we have found that these two values are same. So whether you find Kc or Kp doesn't matter, both are actually same. So the Kc calculation, now it will be concentration of Hi, concentration of iodine and hydrogen. Now in terms of Kc, why it is easier? Because it is mentioned in the question that the cylinder is filled with equal number of hydrogen, iodine and Hi. So if I write that the number of moles of hydrogen is N, for iodine it is N, and for Hi also it is N. And suppose the cylinder is having volume V. So in this concentration expression, I can write Hi concentration is total number of moles divided by volume. So it will be N by V to the power square. Then concentration of H2 is number of moles divided by volume. Concentration of iodine is number of moles divided by volume. So everything will be cancelled and you are left with 1. So now I hope it is understood why I have first determined the relationship between Kp and Kc, because in terms of Kc the calculation is easier. It is not that pressures are mentioned, it is number of moles are mentioned. So if you do the calculation in terms of concentration, that is N by V, it is better. So Kc is 1, but you have to write it in this way. 10 to the power minus 1 and then multiplied by 10, that is also equal to 1. Now you can compare this with the format that is given in the question. So here 10 is the value of x and correct answer will be option 3. Okay. The following reaction occurs in the blast furnace where iron ore is reduced to iron metal. So this is the iron ore. Reducing agent is carbon monoxide. We are getting iron, sorry, it will be S, solid state, and we are getting carbon dioxide. So this is the equation given. Using Le Chatelier principle, predict which one of the following will not disturb the equilibrium, right? First option is saying removal of CO. Now when you are removing CO from the medium, the concentration of CO will decrease. So the equilibrium will try to shift towards left hand side. Towards left hand side, the equilibrium will be shift. Okay, better write in this way. Because to maintain to increase the concentration of CO, just like the equilibrium condition, because you have already removed CO, but the equilibrium, it will try to maintain the same concentration of CO. And how it is possible? It is possible only if the equation is moving towards the reactant side. So this expression, this option, that is removal of CO, it will disturb the equilibrium, and this is not our correct option. Second one is also just like that, removal of CO2. So you are decreasing the concentration of one of the products, but equilibrium, the system will try to maintain equilibrium according to Le Chatelier principle. So the equilibrium will be shifted towards right hand side so that it can increase the amount of CO2. So this is also not our correct option. Then addition of CO2. Now you are increasing the concentration of CO2, but to maintain the concentration of CO2, the equilibrium will be shifted towards left hand side so that more CO2 is consumed. Here also it will disturb the equilibrium and it will be shifted towards left hand side. Only the last one, addition of Fe2O3, because it is in solid state. And when something is in solid state or liquid state, it actually doesn't matter whether you increase the concentration or decrease the concentration. And that is the reason this will be the correct option. Okay. Next question is the standard equilibrium constant for the reaction sulfur trioxide decomposed to sulfur dioxide and half oxygen. Standard equilibrium constant, that is equilibrium constant at standard condition, is given Kc naught 4.9 10 to the power minus 2. The value of Kc naught for the reaction, which is another reaction, but it has some similarity with the previous reaction. What is the similarity? The similarity is, if you look at the first reaction, it is decomposition of sulfur trioxide to sulfur dioxide and half oxygen. But if you look at the second reaction, it is basically the opposite reaction. And it is not just opposite reaction. There is also change in the coefficient, right? So what we have to do, Kc for the first one is given, which is 0.049 Kc naught. You have to find Kc naught for the second reaction from this value of 0.049. So we will try to find out what is the relationship between the value of Kc naught for the second reaction. So suppose for the second reaction, I am writing it is Kc naught prime so that we can understand the difference between these two. So Kc naught prime, it is related to the previous equilibrium constant. How? First of all, it is reverse. And when it is reverse, you just have to take 1 by Kc naught. And it is just as reverse. There is difference in the coefficient also. What is the coefficient difference? If you multiply both sides for equation 1, suppose I am multiplying with 2. 2. Now 2 means it will be cancelled. Now see, it becomes having the same coefficient. So there will be change in the coefficient also. So when you change coefficient, suppose you are multiplying with x, that x will be in the power of the previous equilibrium constant. So it will be Kc naught 2, Kc naught square. Now do the calculation, 0.049 square. And you will see the value will be 416.49, which is closely matching with 416. Okay. So in this way, first you have to understand the difference between these two equations, how you can get the new equilibrium constant. That is, you have to find the relationship between the new equilibrium constant. This is the new one. This is the old one. So the relationship between the old and new, once you know that, as the numerical value of the old one is already given, you can easily find out the value, that is the numerical value for the new equilibrium constant. So option B is the correct option. So this question actually there is 2024, but it is also repeated in that is basically better I say it is repeated in 24, because previously it is also there in 2022. Okay. Here the equation is A is converted to B and half mole of C. 1 mole of B, 1/2 mole of C. In the, so it will be above. In the above reaction, the correct relationship between the Kp value, because all the reactants product they are in gaseous state, then the alpha value, that is the dissociation, degree of dissociation, and then, or you can say degree of decomposition, because here the A is decomposed to B or half C. The equilibrium pressure P, that relationship you have to find. Okay. So how we will start it? We will start from writing the equation. So A is converted to B plus half C. So suppose the initial moles of A is N and these two are obviously 0. That is before reaction, before any reaction. And at equilibrium stage, suppose as alpha is the degree of how much A is decomposed to B and half C. So N minus N alpha, that is the remaining amount, that is the equilibrium amount. Now when N alpha amount of A is reacting, as the coefficient ratio is 1:1, that is the relationship between A and B. So the amount of B is N alpha and the amount of C is N alpha divided by 2, right? Now we can calculate total moles at equilibrium. So total moles will be, just add all this. So N alpha cancelled. So you will be left with N common 1 plus alpha divided by 2, right? Now we will find the equilibrium pressure for all the 3 species. So equilibrium pressure for A. So it will be basically the mole fraction. First of all, you have to know the mole fraction of A multiplied by the equilibrium pressure P, which is given. That is equilibrium pressure, total equilibrium pressure. It is not individual for A, B or C. That is not mentioned here. It is the overall equilibrium pressure. So when you are trying to find out the equilibrium pressure for A, then what we will write? Suppose I am writing here PA. First of all, what is the total number of moles of A left? It is this one. So N common 1 minus alpha divided by the total number of moles, which is N common 1 plus alpha by 2 and multiplied by P. Now if you simplify it, you will see it will come to as NN will be cancelled, 1 minus alpha divided by 2 minus alpha multiplied by 2P. Next we will find out the equilibrium pressure for B. Similarly, PB, look at the number of moles, it is N alpha divided by N common 1 plus alpha by 2 multiplied by P. NN will be cancelled and ultimately you will see the value will be 2 alpha P, 2 plus alpha. Same thing we will also do for C. Now for C it is N alpha divided by 2. NN will be cancelled and this denominator 2 will also be cancelled, and ultimately after simplifying it will be something like this. Now we will calculate the Kp. So Kp expression will be partial pressure of B, partial pressure of C, half, because that is the coefficient. So we will put all the values in the pressure terms. So for B it is 2 alpha P 2 divided by 2 plus alpha. Yes. Then we have within root alpha P 2 plus alpha divided by so after simplifying so here 2 alpha cancelled, then P and there is this P cancelled. So ultimately what is left, and alpha will be having power half and here we have power 1. So alpha will be 3 by 2. P will be half left only, nothing is there. And in the denominator there is this expression, that is 2 plus alpha to the power half and 1 minus alpha. And it is matching with the last, this one I think, alpha to the power. Yes, this one. Okay, so option 4 will be the, so see, correct option. This is not something very difficult, but you just have to do all the steps peacefully. Okay, so if you in a hurry, there is a high chance you will do some mistakes, because it is not something very, that is, you have to be very intelligent to answer this question. You just have to write stepwise, you have to do different things. Okay, that's all about. From that point of view, it is to some extent complex, not so simple. It is some time consuming question, that's it. For a concentrated solution of a weak electrolyte, K equilibrium, within bracket mentioned, it is the equilibrium constant. And the weak electrolyte is A2B3. Concentration is given C and the degree of dissociation is given alpha. So for a concentrated solution of a weak electrolyte A2B3 of concentration C, the degree of dissociation alpha is, so alpha is expressed in terms of, look at the options, K equilibrium C, K equilibrium C. So in all the options, K equilibrium and C, these two terms are present. So you have to find the relationship between alpha on one side and K equilibrium C on the other side. That is the thing that we have to do. So this electrolyte A2B3, how it is dissociated, because it is electrolyte, there will be equilibrium. It is not that it is very strong electrolyte, so all the initial moles will be dissociated. No, there will be some equilibrium. Some amount of A2B3 will be dissociated. So it will be 2A 3 plus. Now if you are thinking how I am writing 3 plus, because from the coefficient, as it is 3B, that means total positive charge will be 3 plus. And 3 moles of B2 negative. So this will be, after dissociation, this will be the expression. Now total positive charge 3 into 2 plus 6, total negative charge 3 into 2 minus 6. So initially, if we have C and these two are 0, then alpha is the degree of dissociation. So C minus C alpha at equilibrium. C common, 1 minus alpha. Now the relationship is, from 1 mole you are getting 2 moles. So it should be 2C alpha. And 3 moles of the NR. So it will be 3C alpha. These are the expression. Now K equilibrium, that will be A3 plus to the power 2, B2 minus to the power 3 divided by A2B3. Now put all the values. A3 plus, it is 2C alpha. So to C alpha directly I can write 4C square alpha square and 3C alpha to the power 3. Now 3 to the power 3 it will be 27 C cube alpha cube divided by C1 minus alpha. So C total power 5 in the numerator, here it is C in the denominator only 1. So finally it will be C4. 1 minus alpha will be there. 4 into 27, it is 108. Alpha square and alpha cube. That means it will be total alpha 5. So alpha 5 you have to bring to one side. So alpha 5 should be equal to K equilibrium. Sorry, here 1 minus alpha, it is actually almost equal to 1. So that assumption we have to do. So instead of writing 1 minus alpha, as it is already equivalent to 1, so simply I will write K equilibrium divided by 108 C to the power 4. And this whole expression, when we are trying to find out only alpha, it will be K equilibrium 108 C4 1 by 5. And it is this 108 term basically you will find only in one option, first option, right? So no confusion. Even you can reach this value of 10, that also will help you to choose the correct option, right? The equilibrium constant for the reversible reaction, the first reaction is given 2A in equilibrium with 2B and C. For equation 1, K1 is the equilibrium constant. Now look at the equation 2, 3 by 2A. Here also it is A on the left hand side and B and C on the right hand side, but the coefficients are different. So 3 by 2A, 3 by 2B and 3 by 4C. This is equation 2. And for this equilibrium constant is K2. You just have to find the relationship between K1 and K2, right? Now equation 2 you can get when you multiply equation 1 with 3 by 4. So when you multiply equation 1 with 3 by 4, suppose I am putting here 3 by 4. What you will get? 3 by 2. Same is also with 2B. Then 3 by 4 of C. This is also 3 by 4 C. So this is the relationship between these two. Now for equation 1 K2 and for equation 1, equation 2 K2, equation 1 it is K1. So as we know, because the concentration of reactant products, their coefficients are always in the power. It is written when we write the equilibrium constant, it is in the expressed as their power, the coefficient. So that is why when you will find the relationship between these two, K2 will be equal to K1 to the power 3 by 4. Okay, and that is matching with option, third option. We'll go to next question. 4 moles of argon. So you have to write the question carefully because there is so many descriptions. You have to write it very carefully. 4 moles of argon, 5 moles of PCl5. So just write it in this way. It will help you, that is pictorially if you express the question, it will help you to have all the information in front of your eyes. So this is present in a introduced in evacuated flux, and this flux is having capacity 100 liter. Temperature is 610 Kelvin. Okay, and so you know the number of moles 4 and 5. So number of moles n we can write total number of moles. Whether reaction is happening or not, we are not talking about that. We are just trying to find out what is the total number of moles, and that is 9. And see, here reaction is not possible because argon is inert gas. How it will react with PCl5? But why we are writing all this Vt and N? Because every information is there, only P you do not know. So if somehow you can find out P value from the equation PV equal to N at T, now you can get the value of P, and that will help you to answer the rest of the question. Now read the second statement. The system is allowed to equilibrate. At equilibrium, the total pressure of mixture was found to be 6 atmosphere. Now the P value that we will get from the ideal gas equation, this is not same as this 6. Because though argon is not reacting with PCl5, but PCl5 itself can do some reaction, and that reaction is decomposition of PCl5 to PCl3, all are gaseous. So this is the actual equation, and because of this decomposition of PCl5, there will be some change in the value of P. So first we will find out what is the value of P initially when there is no reaction is not started yet. So PV equal to nRT. From this, P equal to nRT divided by V. You know N value. Now R you have to express the liter atmosphere unit, which is 0.028. Sorry, 082. 610 Kelvin divided by 100. If you do this calculation, you will find the value actually it is 4.508 atm, but you can express it like this. So this is the value of P, but after reaction it is changing. It is becoming 6 atmosphere. So there is some difference. It is not same as this P, and that has to be, that is expected, because from 1 mole of PCl5 you are getting 2 moles of new gas, PCl3 and chlorine. So that is why pressure will increase. Next, what we have to do, we will find out the partial pressure of this PCl5 and P argon. So this, because this total pressure that you are seeing, that is coming from the combination of air and PCl5. So what will be the partial pressure of argon and what will be the partial pressure of PCl5, that you have to find. How you will do so? Simply find the mole fraction, because you know the number of moles of argon, it is 4. Total moles 9. So this is the mole fraction multiplied by total pressure, which is 4.5. So this is the value of P argon, and this is 2 atmosphere. If you are thinking why I am finding the partial pressure of argon, because ultimately when you will find the Kp value for this decomposition of PCl5, then you will need it. Then PCl5 partial pressure is 5 PCl, okay, let me, 4 moles of argon, okay, 4 by 9. So it will be, yes, 5 by 9 multiplied by 4.5, and this value is equal to 2.5 atm. Now we will go to the calculation of this. So how we will do so? So Kp value, before finding the Kp value, just write the total, that is initial pressure is 2.5 atmosphere for the starting material PCl5. But directly I will write it after equilibrium. Suppose there will be some decrease, and that decrease is P. So I'm writing it P prime because we have already used P. So 2.5 minus P prime, and as the relationship between these three is 1:1, so this will be P prime, this one also will be P prime, right? Now the total pressure, how you will find 2.5 minus P prime plus P prime plus. So it will be 2.5 plus P prime. This is the P total. Now why we have found, sorry, it is not P total, you also have to consider P argon. Because P argon, though it is not taking part in the reaction, but it has some contribution in the total pressure, and that is the reason why we have calculated this one. So it is 2.5 plus P prime plus P argon. So it will be, and this P total is 6 atmosphere, and P argon, what we have found, it is 2. So 6 is equal to 4.5 plus P prime. So P prime is ultimately 6 minus 4.5, and it is sorry, 2.5. So this is also a lengthy question. You have to do it very carefully. Okay, I have done it right. It is actually 2.52. It is 4.5. So 6 minus 4.5, it will be 1.580. Now you know the value of this P prime and you can easily calculate the Kp expression. So Kp expression will be partial pressure of PCl3, partial pressure of chlorine, partial pressure of PCl5. So in PCl3, what you will write? You will write the value of P prime, which is 1.5. Similar is also for chlorine. Now what will be the PCl5 value? PCl5 value is basically this one, 2.5 minus P prime, and P prime is 1.5. So in the denominator it is basically 1. So ultimately it is left, you are left with 1.5 square divided by 1, that is equal to 2.25. So this is the answer, and that you can find in option A, the first option. So how we have solved this? It is a very lengthy question. It is true. First we have calculated before the reaction what is the total pressure, and that pressure is 4.5, which is the because of the combination of PCl5 and the noble gas air. Once you have found it, the next step that you have to do, which is in purple color, you have to find the contribution of air, partial pressure of air, which is 2 atm, partial pressure of PCl5, which is 2.5 atm. Now the third step is reaction has started. Once it has started, you have to write this type of expression in blue color. Then initially it is 2.5, but when equilibrium is reached, it is 2.5 minus P prime and same moles. So that is why pressure term also will be 1:1. P prime, P prime. Now the total pressure of PCl5 after reaction, pressure of PCl3, pressure of chlorine, and also the contribution of PAR. Don't forget it. Once you have written this expression, now you can find out the value of P prime, which is 1.5. Now the last step, the fourth step is finding the Kp value, because now you know partial pressure of the products, PCl3, chlorine, and the reactant, 2.5 minus 1.5. And we got our answer, 2.25. The value of Kc, 64 at 800 Kelvin for the reaction, hydrogen and nitrogen, together it is producing ammonia. The value of Kc for the following reaction, which is somehow related to the first equation, but how it is related? If you can find out the relationship, rest of the things are not very difficult. So for the first reaction, suppose it is Kc, and for the second one, suppose it is Kc prime. Same, not same expression I have used, so that you can differentiate. So the relationship between Kc prime and Kc, that we have to find. So Kc prime, how it is related to Kc? Look at the two equations. The second equation, it is the reverse. The product, ammonia, now it is the reactant. And not just reverse. It is also the coefficients are changed. How it is changed? If you multiply half, see, now it becomes the same coefficient and the second one. So first of all, Kc prime, it will be 1 divided by Kc, and not just simply this expression, there will also be a root. You know the value of Kc, which is 64. So the answer should be 1 by 8. That is option B. Okay. For the reaction Fe2NS 3 by 2 hydrogen gas, we are getting iron metal and ammonia. So in this expression, we have to find the relationship between Kc and Kp. Look at the options, Kc and Kp. Now we know the relationship between Kp and Kc is, you just have to find del Ng value. So del Ng value, in the product side, you just have 1 mole of ammonia. Iron is solid. Reactant side, you have 3 by 2 moles of hydrogen. So your del ng value is minus half. So if you put it here, but look at the options. Kc is on one side. Now if I bring Kc on one side, it will be Kp RT to the power half. That is positive half, not negative. Because here it is negative. So when you change it to the other side, it will be positive. And this is the correct expression. The variation of equilibrium constant with temperature is given below. At 25 degrees centigrade, K1 is 10 for any reaction. The reaction is not given. Temperature 100, now K2 value is increased to 100. Fine. The value of del H naught, del G naught at T1 temperature, that is 25 degrees centigrade. Directly I will convert it to Kelvin because ultimately you have to convert it to Kelvin. It is 298 Kelvin. And temperature T2 is 100 plus 273, which is 373 Kelvin. So you have to find del H naught, del G naught at temperature T1. And for T2, you just have to find del G naught. So three things you have to find. So the first one is the first values because all are in respectively. So the first values are for del H naught. The second one is for del H naught at temperature T1. And the third one is del H naught for the temperature at T2. So here we will use this equation, that is ln K2 divided by K1, and that is related to del H naught gas constant 1 by initial temperature 1 by final temperature. You can also use expression I and F, but here already 1 and 2 written. Now K2 and K1, it is ln 100 divided by 10. Del H you do not know. R value you have to use. Don't use 0.082. It should be 8.314 because that is in joule. 1 by T1. T1 is 298. T2 is 373. So from this equation, if you simplify, I'm just doing straightforward because we are lacking in time. So del H naught, that will be equal to, because rest of the things you already know, you will find it will be 28371.97 joule per mole. But you have to use it in kilojoule per mole. So that is why it will be 2837 or 28.4. Now 28.4, it is present in C and D. Next we have to find what is the value of at T1. Now del G naught, that is related to temperature and equilibrium constant like this. I'm writing it G1. So simply write 8.314 multiplied by 298. You know the value of K1, which is ln 10. You can also convert it to log. So ultimately we will see it is 570482 joule, but we will change to kilojoule. So it is present in option C. Now we even don't have to find the del G2 value because already we have found that option C should be the correct answer. But if we calculate it, it is minus RT ln K2 . .43. So it will be 14281.19. I have written it wrong. Should be 14.28. So it is also matching with the last one. So option C, that should be the correct option. Okay. So we're already at the end of the session. So we will end the session here. Thank you for listening.